Welcome everyone, and today we're honored to have Dr. Liang to have our speaker to talk about multisensory AI. And Dr. Liang got his PhD from Carnegie Mellon University in the machine learning department in 2024, and now he's an assistant professor of computer science, electrical engineering, and computer science, and also in the media lab. And let's welcome Dr. Liang to talk about multisensory AI.
Great. Thanks for the introduction. Hi, everyone. Thank you for coming. Well, let me just get rid of that.
Can we take
Oh, yes, of course. Yes, thanks for coming. So I lead a group at MIT called Multisensory Intelligence. We build AI systems that are able to learn and interact with the world through many sensory modalities. And that's a photo of us over there. We just started at MIT last September. We're young, but also growing very quickly. So we open to all sorts of collaborations with folks here. So our group has three general themes. As I mentioned, we build AI systems, this new generation of AI systems that are multisensory in nature. Think of large language models. They only understand language, but to truly understand the world, you need to understand all forms of data from language, vision, audio, sensors, and more. So we build the science and engineering and practical AI systems that are able to learn through different sensory mediums. A lot of the work in our group is also about building these AI systems for humans. So how can you use AI to process vast amounts of medical data to help humans track their health and well-being? How can you use AI and generative models to enhance a person's creativity by generating better and more nuanced forms of music and dance and more? And finally, because a lot of AI systems that we develop are very closely understanding, sensing, and interacting with people, we also take a lot of extra care to make sure these systems are safe for the real world. So that entails problems from guaranteeing their robustness to different theoretical principles to making sure these systems are fair and accessible to different populations in the world. So naturally, today I'm going to focus the talk more on the health and well-being side of our group's research, in particular, the applications of multisensory AI towards health and well-being sensing. And again, because our group is quite multidisciplinary and we look at lots of multimodal data, we also view health from a more holistic lens. There's projects in a group that are more physical health related, so understanding these physical indicators that you take in a doctor's office. Here's one example, just very briefly, a project where some of my students deploy computer vision systems in the ICU. So we do really fine-grained object recognition and tracking, and it can therefore track whether these patients are at risk, whether they've fallen down, whether they might be in status of emergency, and therefore that can reduce the reliance on doctors and nurses to monitor them 24/7. So beyond physical health, our group also has always been working on emotional well-being. We started this line of work on using multimodal AI systems to understand the person's spoken language and also their nonverbal expressions, like your facial expressions, your vocal expressions, your body language. We understand their mood and mental health. And I'm going to show some examples of how we've applied these systems to do early detection of depression and suicidal thoughts and behaviors in young adolescent teenagers. And going from the emotional, which is a single person, we've also looked at systems that are better able to understand the social interactions between people. So these are systems that are able to look at eye gaze and attention and turn taking to understand the social dynamics between groups of people. And we really think all of these will come together. There's going to be, of course, huge impact of AI towards understanding physical indicators of health. But we only go to doctor's office once or twice a year. There's also a huge opportunity for AI systems to be used on a day-to-day basis to understand emotional well-being through daily sensors and smartphones, wearable devices, the systems that understand how people interact with others. All these really come together to indicate a person's holistic health. So in terms of key takeaways, I'm hoping that the audience will appreciate after this talk that many problems in health and well-being sensing are multimodal in nature. It requires the integration of different sensory modalities, each providing some complementary information. And given that many problems in health and well-being sensing are multimodal, multimodal AI is going to be a very general paradigm that can be applied to many of these problems. And multimodal AI is essentially the science of building AI algorithms that are able to learn from very heterogeneous. In other words, the modalities are often very different, and the differences causes difficulty in processing them together. And at the same time, some interactions between the modalities, some amount of complementary information that comes together to give you new information critical for some task. So in the first half of the talk, I will cover some of our more foundational work in multimodal AI and how they can be applied to various medical problems. And in the second half, I'm going to dive deeper into some of the more application-specific medical problems we've looked at. So as I've probably motivated, the whole goal of multisensory AI is to build AI systems to understand this whole multisensory world. That entails going from language models that understand spoken words to systems that holistically also understand your vocal expressions, your speech, and any facial or body language gestures you might be using to communicate with others. It entails going from AI systems that only are trained on one domain, like X-ray images and radiology, to systems that can holistically process other data forms used in the medical domain, including histology images, medical sensors, and even things like wearable devices and mobile data that gives great indications of daily health and wellness. And that's just a glimpse of the modalities that are out there that AI has been applied to. AI is also being used to study the fusion between different groups of modalities. So in this first part of the talk, I'm going to explain some general principles we've developed for building multimodal AI. In the first part, we're going to start simple and essentially just represent these modalities as triangles and circles. So this is a two-modality case. And Y is some label that we're trying to predict by fusing these modalities together. Now, this is a general problem which we call multimodal fusion. Right? It can be image and text, it can be medical image and EHR reports, any two modalities. I'm going to use these abstract symbols to really hammer down the idea that these methods can be applied to any combinations of real-world data. So in the first part, we'll look at multimodal fusion, ways that we've been studying it, and methods that we can develop to bring about multimodal fusion. And in the second part of the talk, I will go a bit broader and look at going beyond two modalities. So in the real world, you often have many modalities that come in. And at the same time, instead of just predicting one task, there might be many tasks that you want to predict. You want to predict how likely the person have a disease, but also survival rate, length of stay, multiple things. And perhaps this could even be language. But you can ask any question, and the model would ideally give you some answer. So this new set of models, we call them multisensory foundation models. Everyone's probably been familiar with the work in language foundation models. How do you make them actually understand multisensory data and answer your questions reliably? So, but first, starting simple, from multimodal fusion. So at a high level, multimodal fusion describes this problem where you have two modalities and you're trying to bring the information together to see how they combine for some task. And in general, I'm going to use just these circles to represent modalities 1 and 2. Purposely, I show them with some overlap because modalities often have some overlapping information. We think these doctor notes, they often reference some part of the image, but at the same time, there's often information in one modality that is not present in the other, unique information. And I use this third circle Y to represent some task that you're trying to predict. So a general framework for looking at multimodal fusion is firstly looking at cases where the information is redundant. This is the phenomenon where there is some common information that is present in both and that is relevant for the task. So one example is a person might be saying, this movie is great, with a huge smile on their face. And together, you are very confident that the person really liked the movie. And that is in opposition to unique information. There's information in one that is not in the other. So you can think a person might be saying, this movie does a good job developing the characters, slightly positive, but with mostly neutral expressions. And out of these, it's about selecting the one modality with the right information. And the third case is this idea of synergy, when there's some information that isn't present in a modality to begin with, but only arises when you fuse them together. So one example is the person might be saying something positive, like wow, but with anger and frustration on their face. And then you can realize the person is actually being sarcastic about the topic. So this idea of sarcasm only comes about when you compare the differences between the modalities. It isn't present in just the ones by themselves. So a lot of our work has been about coming up with, well, first of all, coming up with this framework, but more importantly, coming up with algorithms that actually allow you to quantify, given two modalities and a task, how much information is redundant, what information is unique, and also what information is synergistic. And we've essentially come up with new information theoretic methods to understand these quantities, which allows you to understand which data sources are important, first of all. If I am trying to maximize performance for a task, which modality should I even collect in the first place? So using information theory to study that. We can also answer questions like which data sources would actually interact together. So which pairs of modalities are meaningful, and bringing them together brings about new information, and therefore you should go collect those two data sources. And we've been doing that especially to study even two modalities. When is there redundancy between them, and when is there synergy between them? So it's worthwhile to bring them together. If it's unique, then you don't need to do any multimodal fusion. And finally, we've also been able to give even guarantees where if you want the model to perform, for example, 80% accurate on some tasks, it will tell you how much data you will need to collect. So that gives you a good guidelines for what data to collect, how many samples do you need? Should I collect them separately or should I collect them together? All these practical questions around data collection with respect to some performance measure that you're targeting. So some of these parts are quite technical, so I'm not going to go into the details, but papers are here and code is up there. So code that allows you to run these estimators. Essentially, these are statistical measures where given some data, it tells you the number of bits of information for each of these quantities. And also it tells you, given some performance, how many data samples are going to be required in theory to reach that performance. But moving on to some real examples. I'm going to show two examples where we've applied this framework in problems related to health and wellness. The first problem is in mental health. This was in collaboration with psychiatrists at University of Oregon, Columbia University Medical Center, and University of Pittsburgh Medical Center. And in this setting, there were essentially these young adolescent teenagers, three groups, so control groups who were fine, a group who were diagnosed with depression but did not attempt suicide, and a group who were diagnosed with depression and had attempted suicide, but failed. So these are three groups, and the goal is to do real-time mood assessment of these three groups. So you can assess their daily mood. You can tell times when they're going to really bad mood and they're going to be at risk, and you can tell that to the psychiatrists. So we really explored these modalities on the smartphone because teenagers bring their smartphones around wherever they go. One modality is the text that they're typing on the smartphones. IRB approved, they've given us access to all this data. And the second modality are the applications and keystroke patterns that these teenagers were using on the phone. So what applications they were typing things in, and keystroke basically says, the pattern of typing, quick, slow, backspace, delete, and it's instead of just the actual words themselves. And the goal, as I mentioned, was to understand, to track in real time the daily mood of these patients and relay that information to the psychiatrists. So you can apply our framework based on the data that you collect, X1, X2, Y. You can run these estimators to essentially get these bar charts, which shows in bits of information how much is redundant, how much unique in language, how much is unique in the applications and keystrokes, and how much is synergistic, so combined when you have both modalities. And you realize that actually there's a good bit of synergy between them. And if you start digging deeper at where the synergy comes from, you actually realize that sometimes the teenagers are typing positive words like love, thanks, and haha. They seem very positive in conversation. If they were typed quickly, that's a good sign of positive mood. But if they were typed slowly, so you might type love, but then you delete it. You type thanks very slowly, hesitating, delete it again. That's actually a very big sign of negative mood. Several other examples. Don't and just. These are reasonably negative words with negative sentiment. If you type them very quickly, that's a sign of negative mood. And if you're typing them slower, it's more a sign of neutral mood. So you really have to look at the words in the context, this very personalized context of how these patients were typing on the smartphones. And it was great because it gave these accurate and more importantly, personalized mood markers that were able to be used to study these patients in the cohorts and relay that information to the psychiatrists for them to follow up and to better treat these patients. Another example, yes.
This is what you learn from your training. For now, thanks, make faster is good. Don't just slow is better. This is what you learn.
Yes.
What is the psychological mechanism behind this? Is this the real thing, or you just happen to find those seconds?
So this is what we found from the data. I'm not a psychologist, so I don't know what is a psychological reason behind these different typing patterns, but this is what we found in the data. There were several other, these were to us some of the things that were interesting to the psychiatrists as well. There were several other indicators that, as you put it, more known in psychiatry. So what time you use your phone, like right before like bedtime usage, like binaural usage of the phone, that was something that is known in psychology to be a big indicator of poor mood. And we also found that was reinforced in the data. So there were several cases where these known concepts were reinforced from the data. And there's some of these which were more interesting. I don't think we have an explanation for it, but these were indicators that we found in some of these patients. Again, we didn't say this is a general thing. So these are very personalized. One person displaying this pattern and being indicative of their mood does not really also indicate this is a general pattern that all teenagers with depression would exhibit. Great. So another example that I want to highlight is in the pathology space. These are some collaborations with Harvard Medical School and Brigham Women's Hospital. And in this case, we are looking at histology image and genomics profiles in order to understand the survival rate of different types of cancers. Again, a commonly studied group of modalities, been very popular recently. And again, using X1, X2, your data, and your task Y, to run these estimators for different types of cancers. So for glioma, brain cancer, you actually find that primarily unique information in genomics was the most indicative of the survival rate for that cancers. For pancreatic cancer, we actually find a lot of synergy between histology and genomics interaction. And therefore, when you start training these machine learning models, so you can train convolutional networks or vision transformers on the image, you can train sequence models on genomics separately, and you can also combine those models together. We find that when you're doing pancreatic cancer, there's up to a 15% performance improvement when you do multimodal fusion of histology and genomics. And that's explained by the information of synergy within those two modalities. Whereas for glioma and brain cancer, you could train these multimodal models between the two of them, and it wouldn't show any performance improvement because all the unique information in genomics was contributing to performance. So again, this was reasonably understandable, and some of these multimodal models were done in collaboration with pathology department here. So that's at a very high level, first part, introduction to multimodal fusion. Given two modalities, looking at the different ways that information comes from, understanding that information, and using that to better understand when different modalities and their fusion would help for some task. I might realize that, again, this is a quite simple setting. Everything has still been looking at just one element in each modality. So we look at one word or one gene expression or one image. But in the real world, we obviously have extension to multiple elements. You often have words that a person is speaking across time, or entire sequence of genomes, or even video or very large images that have to be broken down into individual parts. So in the second part, we're going to look at these more sequential models that are able to deal with data that has multiple elements in a sequence. I'm going to use some of these videos to motivate. As you can see, a lot of our work has been in human behavior, so I'm just going to show a quick video.
It's just a privilege to watch your mind at work.
Everyone got that? Let's play it again.
It's just a privilege to watch your mind at work.
So you recognize this from the Big Bang Theory. Actually, we in the AI space, we work with a lot of YouTube data, and Big Bang Theory is a good example because it has lots of different expressions of humor, of sarcasm, of friends and relationships between different people. So it's been a great test bed to study social interactions. As you see in this video, Sheldon is, it's such a privilege to watch your mind at work. And clearly it's not a privilege, he's being sarcastic to his friend. So we've developed these multimodal transformers. They're quite popular nowadays to essentially learn from this type of sequential data, things that a person is saying across time, facial expressions across time, and so on. And so I'm going to cover, the basics of these multimodal transformers. This is a scary equation, but I'm going to go through this step by step. So the first thing here that is critical is what I've highlighted in purple. So X1 WQ. So X1, you can essentially think of that as your data. So in this case, your data is 3, because for simplicity, I'm assuming that let's just say they're saying 3 words. Privilege to what mind at work. Right? Everything else is kind of stop words, not very useful. So 3 words, and D represents the dimension of each word. So these are features that you're extracting, telling you the features representing each word. So that's 3 by D, and WQ is essentially some linear transformation that you can learn. And most of machine learning is about learning these parameters that are linear and non-linear features from your data. So that's the first modality, language, 3 by D. And then the second thing in yellow is your second modality. So here is D by 4. You can see the matrix transpose over there. So it's the other dimension. You first order the dimensions first, and then you have 4. In this case, this person is showing 4 steps of nonverbal expressions. For example, something voice, just like a loud voice, privilege, loud voice, showing an eye roll at the end after speaking a sentence. So 4 steps of your nonverbal expressions. And the key idea behind these multimodal transformers is we essentially do this outer product multiplication between your 3 by D verbal and your D by 4 nonverbal. And that outer product essentially gives you something that is 3 by 4, right? The D dimensions are multiplied with each other and becomes a number, and therefore it's 3 by 4. And you can interpret these 3 by 4 matrices as an attention matrix. It's telling you, in this case, between vision and language, how much each of my 3 words should be interacting with every one of my 4 nonverbal expressions. Some of them are going to interact more because that pair is very informative when taken together in context. Some will interact less. So it's a 3 by 4 weighted outer product, and weighted by your WQ and WK. These are your learnable parameters in the model. And then you do the square root of these or normalization. As I mentioned, each of these entries in your 3 by 4 matrix is a d-dimensional vector multiplied by d-dimensional vector. So the magnitude of that number scales with the size of d. So you renormalize by square root of d, so the variance goes back down by 1 over d. And finally, a softmax, essentially this operation, again, normalizing function that normalizes every one of these rows into values that are non-negative and sums to 1. So making it non-negative and sums to 1 means that you can essentially interpret these numbers as elements in a probability distribution. So privilege might interact 0.7 with vocal emphasis, 0 everywhere else, and interact 0.3 with eye rolling. Mine might interact 1 with vocal emphasis and 0 everywhere else. So each row is non-negative and adds up to 1. So you can view it as a probability distribution. So these are the key ideas of in the single modality large language model case, we call this self-attention. In the multimodal case, where your data is coming from 2 modalities, we call this cross-modal attention. And this cross-modal attention can then be actually multiplied with the actual features. And you want to think of this multiplication as essentially creating a new set of representations for the words where each word, for example, privilege, is looked at 0.7 times the vocal emphasis feature plus 0.3 times your eye rolling feature. So it's a weighted summation across your nonverbal features where the weights are given by these attention scores, right? So we also call that, contextualizing language with vision, or learning a new language representation interacted by fused with the other visual features. And of course, that gives you a new multimodal representation that can be used to predict, in this case, sarcasm. So there's multimodal transformers in a high level in one slide. Again, papers are here, code is there for people who want to try these out. So we applied multimodal transformers, when we started doing this in kind of 2019, 2020, we applied them to many settings of human communication, language, words a person are saying, facial expressions they're making, vocal expressions like anger, loud, not speaking, or speaking slowly or quickly. And we can use that to predict things like sentiment, emotion, sarcasm, humor, all aspects of human behavior. Now we have some collaborations in applying this to understanding mood and depression from videos of people, even autism, right? Looking at young children and the videos of them talking to therapists, understanding whether they might show early signs of autism. It's also been quite popular in the community. These multimodal transformers have essentially formed the backbone of many of these large vision language pre-trained models, vision language models. So here is, I'm showing an example from Google's model, DeepMind's model, where again, you can essentially give it language by talking to the model, typing something, you give it an image, and what the model is doing internally is that it's breaking down each of the words with pixels in the image, and it's applying transformers to learn these cross-attention representations. So this is an example of the Stroop test. People recognize, given an image, can you recognize what it says and the color that is written in? So the first one, it says purple, but it's written in red. And it says green and it's written in blue. Here are two examples that the model can start completing the answers for new images, and even recognizes that it is a Stroop test. In the medical space, we also apply these multimodal transformers. Again, this was with pathology. You have these histology images that are really high resolution. So 69,000 by 87,000 pixels. Normal computer vision works with 512 by 512 or 1024 by 1024. So this is really high resolution. Cannot train a single convolutional neural network or neural network to process this image. So you can break it down into a sequence of local patches, each of them more reasonable in size, 256 by 256. So those patches across the image. And then you have a sequence of patches, and you might also have a sequence of the gene expressions, or the genomics data. And you're going to start applying these multimodal transformers essentially between your sequence of image patches as one modality and your sequence of genomic expressions in the other modality to predict risk. And these models work well, and they're also reasonably interpretable based on the attention scores that they learn. So it's learning all possible pairs, but some of these attention scores are going to be higher than others. So one example of attention with a very high score we found was this EMT genome, which I guess is known in cancer to be quite indicative of how strong these tumor cells invade nearby cells, are aggressive to nearby cells. So that was a genome important information, and at the same time, it had learned the relationship between parts of the image highlighted in red, which is high attention scores highlighted in red, and these parts of the image were actually showing these tumor cells invading these healthy cells. They're able to learn this relationship between the genome and parts of the image. And nowadays, we've really been scaling these multimodal transformers up. Almost any modality can, at a first order approximation, be seen as a sequence. Right? Language can be seen as a sequence of words. Speech can be seen as a sequence of frequencies. Sensor data can be seen as a sequence of time steps at each time step. And therefore, you can essentially train these unimodal transformers within a single modality. So that will learn how each word interacts with other words in the same modality within the same sequence. And these multimodal transformers, so it can learn the relationships between the words in the sequence with parts of the image, or words, time steps in your sensor data, with entries in your table. These are very general purpose ways to learn relationships within and across different modalities. So there's some work in essentially scaling up these multimodal transformers. In our work, we've shown you can define the same architecture and even with the same parameters. So it's the exact same model for a lot of things. It can understand these videos, as I shown. It can understand figurative language between image and text, humorous language between image and text, sensing data, and even robotics data. So it's a single AI that with the same parameters, these are transformer-based models that can do multiple tasks at the same time. Again, papers are here and code is available. Yes, so this is a model where essentially we're taking multiple different tasks that seem very different. So there's some tasks with human videos, there's some multimedia data, there's some robotics data, there's some healthcare data, and they all seem to be very different, but they share this common set of modalities, right? And we've shown that you can train essentially a model on everything. So the same model is able to understand videos of humans while understanding data on the internet, while understanding medical data, making predictions on all of these at the same time. And it's as competitive as methods that were trained in isolation on each of these separate domains. Yeah.
So, based on my understanding, you are saying that even the training rates and one model can work for multiple.
Yes. And also multiple modalities. So one
is there must have a certain modalities or just is flexible
well, these were the ones that we studied. So first, if you fix the modality, let's say language, you train a model on language and you do multiple tasks, we know that that is possible, right? Like these large language models and even BERT-like models were able to do this. And now we are saying you can do multimodal inputs and multiple task outputs. So in the input side, sometimes you might have language and like humans, right? Human language and human facial expressions. Other times you might have language and other forms of images. So this is the common set of modalities that we are looking at. And the key assumption here is that we essentially take everything and we convert it to a sequence. So language is sequence of words, image is sequence of patches in the image, sensor data is sequence of time steps. And once you treat everything as a sequence, these transformers are able to work on basically anything that is a sequence. And it is competitive with even some of the very specific things, domain-specific methods you might design for sensors. Great. So in just the last part, the last part very quickly, we've been doing applying some of these huge multimodal input, multitask output models in the healthcare space. So again, this is some resource that we've created, led by my student. It's called CLIMB. It is a massively multimodal, multitask clinical data resource, where we essentially collected basically all the publicly available medical data sets that are out there on the internet. So that includes 1D data, for example, there's ECG data sets, EEG data sets, genomic information. 2D will be all your 2D imaging, like pathology, X-ray, CT. 3D will be your MRI, ultrasound, endoscopic videos, so more video, and graph will be molecules and biological graphs. So these are all the info modalities from all the publicly available clinical medical data sets on the internet. And of course, these are annotated by different tasks. Some are about understanding cancer, some are about doing COVID-19 prediction, other lungs, pneumonia, and so on. And once you start centralizing, you're essentially getting a very rich data resource where you could explore at a very large scale these problems of training large multimodal and multitask models. And of course, you also get other good benefits like geographic diversity. So you could essentially build models that work across all regions because your data was collected from all regions. And we also make it super simple to essentially load any data set, reducing significantly the barrier of entry to anybody who wants to build AI models for healthcare data. So in just a couple of lines of code, you can load any data set or any combination of data sets within within everything here.
Before you meet, there are some features between these data sets. For example, the patients are staying in some of them because they're taking on multimodality. So is there some ranges or meta information? I mean, if we load the X-ray data set and also patterns data,
Yeah.
so are they coupled about?
They will not be coupled. These are all separate data sets that everyone has collected, and we credit all the original contributors, but there's not gonna be one patient where you see all of this. I mean, it'd be great if we could. But the good thing is we have models nowadays that don't require pairings to still do multimodal and can still do multimodal fusion. Right? You might see X-rays from one hospital, X-rays from some other hospital, and perhaps you might even see X-rays and CTs. These are both imaging data. There's a path towards a vision model that can understand X-rays and CTs together, or EEG and ECG together. These are all sensor data. So those are the kind of questions that this data resource enables us to study. So speaking of questions, this is kind of a general training and testing pipeline. So as we mentioned, grouped into graph-based data, 1D data, 2D imaging data, and 3D imaging and video dimension. There's 3 general encoders that we believe are going to be sufficient. One is a time series encoder. Anything that is 1D time series based. It can be any sensor or EHR sensor or ECG sensor. One graph-based encoder, and we're hoping that is able to deal with any form of graph data, and vision encoder, which we believe one vision encoder should be able to deal with both 2D imaging and 3D imaging. Okay, so those are 3 encoders. There's 2 training paradigms to study. One is fusion, so you want to combine groups representations from these 3 encoders, and also transfer. So if you train a model, for example, on all of these 9 imaging data sets, you train a vision encoder, does it transfer to some other imaging task also within the imaging domain? And finally, these downstream tasks include things like diagnosing diseases and understanding patient risk. So 3 research questions that we studied. First is a multitask problem. So can you do multitask pre-training within the same modality? Everything here is all imaging, it's just different types of imaging problems. Can you train a multitask model across different forms of imaging data and have them all work on these imaging tasks at the same time? Ideally, it would perform the best for tasks which are understudied and with less data, and leveraging other imaging with more data. So here are some results. So over here, 0 is the baseline performance, and positive is essentially multitask training helps on those data sets, and negative is when multitask training hurts performance on those data sets. So I personally don't know what all these data sets are, but it seems like there are some cases where it helps significantly. For example, COVID US, it helps significantly, and there are also cases where fundus, I think, retinal fundus maybe, where this multitask training can actually hurt. But it's quite interesting to see that there's one single vision model across all of these like 20, 30 vision-related medical tasks has some promise. So there are actually a good number where performance improves. And we also further studied cases where, so in the colors, we're showing cases where it improves and what type of task it is. either a novel task. So we define this as people haven't really worked on that task and the data set doesn't have that many citations or follow-up works. So that's pretty novel. Understudy modality, there are certain types of imaging that is less used than others. Underrepresented regions, some are outside of the US, outside of the Boston area, which is very overrepresented. There's multiple categories where the label space is just very, very big. So positive indication that there's cases where these things really help. So that was multitask. The second question that we studied was transfer. So a multitask, you would train on, for example, 3 imaging data sets and you would test on the same 3. Transfer studies training on 2, and you would test on this third one. Right? Given very, very few samples from the third one, can you very quickly transfer information from the first 2 to the third vision data set? And again, here are some of the results. Essentially, we're showing 2 colors over here. So over here, PT is pre-training. So you can essentially pre-train on Klein, which is our data resource, or you could pre-train on standard data sets. In some other work in literature, building vision data sets. And you realize that if you pre-train on our model, it actually gives you richer representations that across the board give you better performance when transferred to each of these tasks. So some of the biggest improvements are, for example, in ultrasound, get a lot of improvement. On CT scan, it does much better as well. And on chest X-ray, you don't see that much improvement, mainly because chest X-ray has already seen a lot of pre-training and there's a lot of public vision data sets for it. So multitask training is actually quite promising. And over here, we're showing the examples for EEG and ECG. Again, pre-training on Klein, which is in pink, shows better performance than pre-training on other tasks. And in fact, even just using this number of shots here indicates if I want to get it working for this biopsy EEG task, if I give it 1 example, what's the performance? If I give it 8 examples, what's the performance? If I give it 32 examples, what's the performance? So oftentimes, even just 8 or 32 examples from this new data set is enough to get the model working pretty well. And the third question that we study is this multimodal problem. So in the first 2, it was still very much unimodal. It was within just vision. But now we've seen you can do multitask training on multiple vision tasks and multitask training on multiple time series tasks. Now there's some tasks that involve fusion of imaging and time series. So mimic data set is one example where there's medical images and there's ICU sensor recordings and also doctor notes. So you have these multimodal tasks. And the question then becomes, if you kind of take these unimodal pre-trained models that we've pre-trained and you start doing fusion, does it do better on these fusion multimodal benchmarks? And again, we see some promising evidence of this. So SOTA is just prior state-of-the-art multimodal methods on Mimic 4 data sets. Ours are models that encoder representations that we pre-train on our stuff. And in general, it performs better. But of course, it still depends on what kind of fusion strategy that you do. So how you fuse those pre-trained encoders. So whether you do late fusion, use a multi-layer perceptron, neural network for fusion, or cross-attention is the transformer stuff that we discussed to fuse the representations from your modalities. Great. And finally, and I want to emphasize all of this is really, just ongoing work under peer review and something where ongoing work where we're just getting results. So still working on this. And this final part here is everything I've discussed so far was mostly about perception, right? So can you identify the disease or can you determine the length of stay? Nowadays, we see a lot of interest in reasoning. So reasoning means taking all your data instead of just making a prediction, a number, 24 hours length of stay, or here's disease. Can you also explain their predictions? Can you also justify maybe by highlighting parts of the image data that was useful in making that prediction, or highlighting parts of the sensor data? Can you cite medical evidence? Can you perhaps even explain counterfactuals? Right? If the person asks, what if this person was a different age? What would the outcome be different? So perception, well, just give you one number. Reasoning actually requires this more general natural language interaction and understanding with the model. And again, this is some very preliminary work. We're working on these systems that are able to perform multimodal reasoning, where you might be given imaging data and some modalities, learning multimodal representations, maybe using transformers, but then it's able to also explain. For example, it might explain that, lung opacity is some concept that's very important, but there's no obvious areas of consolidation in the lung field. So we're highlighting that to justify the evidence. And maybe as a second step, I'm trying to diagnose pneumonia. There's no signs of inflammation. And again, highlighting part of the lung that was used as justification to show that there was no signs of inflammation in the lung. So we're kind of building these multimodal vision language reasoning models on top of the Climb data resource that I just showed. All right. So I want to just wrap it up there. The key takeaways are that many problems in health and well-being sensing are multimodal and therefore require treatment using multimodal AI methods, which really study the science of heterogeneous and interacting data. In the first part, we looked at problems of multimodal fusion, where you have two modalities and you're trying to predict some task Y, and looking at where the information comes from. In the second part, we looked at examples of building these new foundation models that can take in many modalities, predict many tasks, and even converse in natural language to reason about these tasks. And that's a summary of what our group does. And happy to take any questions. Yeah.
And I just wonder, what will be the effect of using the
Great question. So we actually do have some recent work and a lot of ongoing work on these multimodal mixture of experts. In fact, I like this work a lot. Remember, I was over here discussing different ways in which modalities can fuse together. It was super intuitive, natural to design not one single model that does the fusion, but individual expert models that are each in charge of some type of information. So you could think of one expert model that is exploiting the redundancy, one expert model that selects the unique information, and one or maybe even multiple expert models that do some synergy and fusion. So that's very intuitive. And in fact, we had a paper last year on this. Still, I think it deserves a lot of more exploration. What we did was mostly at a small scale, more supervised learning. But I think personally, these multimodal foundation models that are coming out will probably be a mixture of expert models, right? It's already been very used in large language models. So there's several different experimental settings that we showed. In this first setting, and they're all slightly different. So in this first setting, where we're not using all 4.5 million, we're just looking at the imaging subparts, which is majority, probably 3 million imaging from different tasks. And you would train basically a vision model in a multi-task fashion on all of your imaging related tasks. And then on the training set of these imaging related tasks, and then you would evaluate on their evaluation test set of those imaging tasks. So you train on all 10 and you test on all 10. And then the goal was to show that compared to just doing individual learning on each of the 10, does the performance go up or go down? Right.
Because for example, how about data, there has the members of data in technology or other communities to design some strategies to pilot or
No, yeah, these are all great questions. This was, we didn't investigate too much. I mean, there's a lot of work in multi-pass learning on how to balance data when one has much more data and one has much less. There are ways to do that. We didn't explore that much. This was actually pretty standard. We just tried a few times multi-pass learning, and it was already kind of promising. I think if you do more sophisticated methods, ideally performance will get even better.
because, for example, if here has has a lot of data,
Yeah.
and another one has a small data, that means the model can remember the smaller.
Yes, but at the same time, it is also the opportunity for the model. If you just, I mean, one class is very limited data, you just did supervised learning on it, the performance will be very bad. Right, but if you give these larger, also imaging data sets, then the model would do better. So in fact, some of these ones that the model showed most improvement on were exactly ones with limited data.
And the model is trained from scratch or based on some training models from.
I believe this was initialized using like Chexpert models, so chest X-ray. Yeah. And then we also had some experiments we initialized using the MET-DIT, that's so visual transformer based models. Yeah. Well, I mean, this is not that large compared to LLM training, so it's just like 4 million. So our group has So our group has 8 H200 GPUs. So that's, I mean, and then MIT has some more. You can queue like 5 A100s, B100s at a time, but not H100s. Yes.
I'm not sure I fully understand the difference between the modality and sensor. So, because your diagram had two parts, one more part first is the modality, second is the sensor.
Yeah.
So, what's gonna be exactly the definition of the sensor? So, for example, for a multi-view, for example, video capturing, each view is gonna be interpreted as the sensors, or it's gonna be still just one modality. So, for example, between this, a patient has two, for example, CT
Right.
scan,
Right.
but one from maybe each time for different reasons. So it's gonna be interpreted as a sensor, one sensor, or
Yes, yes. I get that question a lot as well. I don't think, well, first, there's no definitive answer. Also, the answer is not that important in the sense that these are just different data sources, right? Different data distributions that come in. Two views can be thought of as two different modalities, and language and image can also be thought of as different modalities. The key idea is just whatever two modalities that you decide on, they're going to have different spectrum of how heterogeneous and how different they are and how much they interact. So there's two views, then it's mostly homogeneous because both are imaging, but they'll still interact in some way to give you complementary information. If you have image and text, they're going to be much more heterogeneous. They may interact in different ways. So regardless of what, it's just, you can just write them as random variables, x1, x2, can be anything. You just have to deal with heterogeneity and these capture the information between them. Yeah.
Regarding more AI, so do you have any suggestion for accessing the over reliance risk? For example, so AI models may learn hard on one modality to compensate another modality's value. Yeah, because modality, they could be different level of voice, different modality. Say vision, imaging is more clear and it's less ambiguous, but audio can be because they have they pronounce some word that can mean different things. Yeah. So,
Yes. Yes, I have a lot of resources. So, I mean, we teach a whole course on multimodal AI, and we also have 100-page kind of short textbook or survey paper. And we cover a lot of methods. We cover, one section of methods, which is exactly as you described. How do you do this balanced optimization, right? It's very entirely possible. And there are also cases where multimodal doesn't work because one of them is super easy to learn, and then it just ignores the other one. It's very common in the class we looked at. We did a lot of work in human videos. So language is 70%. Now you just say if you're happy or say if you're sad, and then the model just focuses on language and doesn't focus on the subtle expressions or gestures. So it stops working when a person doesn't say anything. There are ways to balance training. There are ways to adapt the other modalities as a secondary input and have language as a primary. There's ways of doing dropout, where you purposely drop out what is the most important and you force the model to look at the others. There's ways that you can modify the optimization algorithm to modify the gradients so that it's scaled by different factors and better optimize the training. But yeah, I think the course and the survey paper that we have covers in detail a lot of these types of methods.
ask this question because it seems that maybe the trial and error is the best way to determine which modality should be.
What does that mean?
I mean trial and error.
Training error?
Yeah. Trial and error.
Trial and error. Yes and no. I mean, if you have already all the data, and then you have a lot of resources, and you are able to try all combinations, then by all means. But usually, you don't have all the data. So especially in this medical space, you have to even decide what data you collect first. Do you put the sensor, or do you collect the video? Do you do audio or no audio? So you have to decide all these things even kind of before collecting the data, which poses a challenge. And sometimes you also cannot try fusing all combinations, right? There might be too many. I mean, it really just depends on the situation.
And how this related to the concepts in the computer system? It's about the synergy and the whole concept.
Yes.
They can be positive effect on synergy, but also there's some compensation and they alleviate the effect. The combination leads to worse results.
Yes, absolutely. So this is all, well, this is mostly theory, right? So I'm saying if you have a distribution x1, x2, y, in theory, this could contribute 5 bits of synergy towards y. Whether those 5 bits are realized when you build a model will depend on many things, including what architecture, how you do the fusion, how you train it, whether you have actually enough samples. So these are all things which might prevent you from actually capturing a full 5 bits of synergy. So you are absolutely right in saying that there's the benefits, but you have to balance it with all these. You need more data, you need more compute to actually do the training. These are all great research questions. Yes. Yeah.
But can we use the mobile or the bus drive another?
Yes, of course, yes. I think it's really everything. So I use the word because when if you go to any AI conference and you say multimodal, people will think of language vision. And maybe nowadays there's some people who work on like audio and video. Multisensory, I like to think is broader. So we can, as exactly as you mentioned, we can include all these wearable, medical, robotic sensors, like everything in the physical space, everything in the climate, all this. But in essence, yeah, same stuff. Same, I mean, a lot more things and a lot more research questions to tackle, but in general, these are still just problems involving different data sources and how they relate to each other. Great. Thank you for the very enthusiastic questions. Sure. Okay.